Now, we have derived the relation between the surface charge density and potential. Now, through that we can establish a relation between the zeta potential and the surface charge density. So, a relation between sigma s and zeta potential on the interface. Now, the Poisson-Boltzmann equation, which we have already derived, that means what we have to give a little bit of revising the previous assumption, that in the Poisson-Boltzmann equation for the electric field, what I did is we have assumed that the ions are distributed by the Boltzmann distribution. That means the equilibrium condition. That means there is no normal flux on the charged surface across the charged surface. So, if you have a charged surface say x, so there is no normal flux of the ions across this charged surface, so y, and also the fluid convection is assumed to be 0. So, with that what we have already derived is the Poisson-Boltzmann equation for electric field, for electric potential, is given by we have d2 phi dx, okay, dy2 in this case, because here we have taken the y as the normal direction. This is equal to 2f c0 sine hyperabolic f phi by RT. So, here we have of course taken these binary electrolyte, symmetrical electrolyte, monovalent also. So, that means Z1 equal to minus Z2 equal to 1, but of course, we can take as this also valid if you have Z1 equal to, it can be also Z1 equal to Z2 equal to Z. So, that is currently a Z or Z hyphen Z electrolyte situation. So, here there will be a Z will appear in this situation. So, for the sake of simplicity, we have taken the monovalent situation. Now, if I apply the Debye-Huckel approximation, so that means what we have assumed is that the phi is less than RT by F. So, with the Debye-Huckel approximation, we get d2 phi dy2 equal to 2 c0 f square by RT or T into phi, but what is the epsilon E? So, there is something epsilon E will be there. So, rho E, because this is epsilon E. So, there is a epsilon E will be divided. So, this is epsilon E, this is the net charge density. So, if I divide, so that is the one. So, now if I define the, which is already introduced, the Debye layer thickness lambda square, where lambda square, as you remember, lambda equal to which we have defined already, epsilon E RT by 2c0 f square root over, this is the lambda square, is also referred as 1 by kappa, which is the inverse of the Debye length. So, in that way one can write the solution as phi equal to a to the power x by lambda plus b to the power minus x by lambda. Now, if we have a situation that phi is tending 0, let defy dy on y equal to 0 is given by, on the wall is given to be sigma s by epsilon e, and on this is y, on y equal to 0, and phi is the equilibrium potential is tending to 0 as y tends to infinity. So, in that case, so the solution, so if we do the a is straight away 0 and b comes to be, if I take the derivative and all, so the solution become phi equal to lambda sigma s by epsilon e to the power minus y by lambda. So, phi comes to be lambda sigma s epsilon. Okay, let us go to the next page. So, phi becomes lambda sigma s by epsilon e to the power minus y by lambda, where sigma s is the surface charge density. Now, sigma s is the surface charge density. Now, if phi equal to zeta on y equal to 0, so what we can write is a relation we can establish that zeta, the surface potential, is lambda sigma s by epsilon e. Okay. So, this shows that this is the relation what we can talk about the between the surface charge density and the zeta potential. Okay. Now, here one interesting thing is that this equation, this relation, if I talk about, so lambda is the Debye layer, Debye length thickness. That means, if you have a surface which has got a charge density sigma s, so you have a layer, say this is the length of this layer we estimated as lambda, which is we call the ideal thickness. So, beyond which the effect of this sigma is tending to be 0. So, that means, this phi is becoming very negligible when y become lambda. So, the Debye length, so we can write that Debye length lambda is the screening length for of the surface charge sigma s. Of course, here this is the equation star is based on the assumption that we are taking a monovalent. Of course, monovalent is not going to make any difference, but binary symmetric electrolyte, and also what we have considered is that the Debye-Huckel approximation, that means the surface charge or surface potential is quite low. Now, one deduction from this relation, if we call this relation double star. So, from the double star there is the relation between zeta and lambda. What we can see that where if lambda is low, lambda less than 1, or normally that is the case, lambda is quite low for lambda 1 or thin Debye length, this zeta is low at a fixed sigma s, the surface potential is low. So, that means it is screened heavily. Now, one point to be remembered that this relation is for a flat surface. We have considered a flat surface because we have taken the Poisson-Boltzmann equation in only one direction, that means is the along the direction y. So, this is valid for a flat surface under the Debye-Huckel approximation. Approximation under the Debye-Huckel approximation with for binary symmetric electrolyte. So, obviously, what we can see conclude from here that there is a definite length beyond which this sigma s is not visible. So, if I go far away from the wall or far away from the distance lambda, so sigma s has 0 effect beyond this. And also you have the zeta potential or the surface potential, and sigma s is related by this way. So, as lambda is low, fixed sigma s, your zeta potential is becoming low. So, this is the way one can characterize the Debye layer. Now, I will show the slides in the slides where the Guy-Chapman model is discussed. So, the slides over here. So, now one can assume the Debye layer is a forming on the surface or charged surface, over which there is a rapid change in the ion distribution. And so, this is the one which proposed by the Guy and Chapman. So, Guy and Chapman considered that a thin layer over which the electric potential within this layer is governed by this Poisson-Boltzmann equation, and the ion distributions are governed by the equilibrium Boltzmann distribution. So, that means, in the assumption is that the no penetration or no flux of ions on the vertical direction across the Debye layer is assumed to be 0. And so, the diffuse double layer, or is also referred as the electric double layer, which forms on a charged surface embedded in a dielectric medium. In the diffuse double layer, the counter ions. So, here we refer the counter ions, the ions of opposite negative charge of the surface are attracted to the surface, and co-ions are repelled by the surface itself. By it, a distribution of ions are governed by the Boltzmann distribution of that is flux of ion is 0, and the along with the direction normal to the surface for binary electrolyte. So, this is the way one can describe the Guy-Chapman model. Okay. So, now we are in a position to formulate the electroosmotic flow over a charged surface. So, in the beginning we have already described that when you have a charged surface. So, when you have a charged surface over which embedded in a electrolyte, say if we consider this situation. So, an electrolyte is filling the two charged surface which are infinitely long, let us assume, and this configuration is referred as the slit microchannel. So, the slit microchannel formation. So, that means you have two parallel plates of constant surface charge density or constant surface potential phi equal to zeta, and so this is phi equal to zeta, and this is phi equal to say some values. So, maybe both are charged or both are same charge or maybe different charge, and a dielectric medium is filling the interior. So, this is also called the slit microchannel. Now, we consider the liquid flow within that. Now, we have assumed a parallel flow. So, that means flow is only along the x direction along which the electric field is applied. Say electric field E0 is applied, and we call this is as the x axis, and perpendicular to that we refer as the y axis. Okay. So, normal to that direction is the y axis. Now, the situation we are considering is a fully developed situation. So, that means the gradient like del x, that is alongside the variation this direction x direction is can be treated to be negligible, which is the condition for the fully developed situation. Now, you see the continuity equation. So, continuity equation, what we find that del u del x equal to 0. So, this implies that you have only u is a function of y. Okay. So, that means the momentum equation, if I now dropped the pressure term is dropped, because here there was no external pressure gradient. So, dp dx, so it should have been a dp del x, which we have taken as 0 because no external pressure gradient is imposed. So, flow is only driving mechanism is the electric field. So, flow is driven only by the electric field, and we are considering this is x and this is the y direction. So, we have the momentum equation for x momentum equation, or momentum equation for along the x direction is covered by this equation. This is basically the viscous diffusion is balanced by the electric body force. Okay. So, this represents a balance of the electric body force term with the viscous diffusion. Rho e is the charge density and phi is the electric potential. Now, electric potential are governed by two mechanism. One is we have considered an applied electric field E0. Another, because of this electric field, the ions, there will be a movement, and this movement of the ions will induce a electric field that is caused by the surface charge of the wall or surface zeta potential. So, that means there are two component of electric field, one because of the external electric field E0, which we have taken as along the x direction. Another is the induced electric field induced by the surface charge. So, we assume a superposition of these two electric fields. So, that means we take phi equal to phi minus E0 x. E0 minus E0 x is the electric potential due to the electric field along the x direction E0. So, we get the net electric potential capital phi we are defining, this phi equal to phi minus E0 x. So, this part, that is the electric field which is induced by the wall charges are now to be solved. Now, electric field at any point is satisfy the that is called, this is not the Boltzmann equation, this is the Poisson equation. We have not so far come to the Boltzmann equation. So, it is not the Poisson-Boltzmann equation, it is simply the Poisson equation. So, Poisson equations, it satisfies this equation. So, which comes out to be d2 phi dy2 equal to this way. Here we have taken a fully developed UF, fully developed situation. So, that means all the gradients with respect to x are, then the variation of the variables x, u, phi are neglected along the x direction. So, this Laplace equation del 2 phi d 2 phi can be brought down to this form, del 2 phi del y 2 equal to minus rho e by epsilon e. Now, the induced electric field we have assumed to be, so if I say the induced electric field is assumed to be independent of x, and this is valid, we can write this way for a fully developed case. We now consider the valid for a fully developed case. Now, we consider the monovalent symmetric electrolyte, that is a situation Z 1 equal to minus Z 2 equal to 1. So, that means the electrolyte are containing cations and anions. So, the ion distribution is we assume to be governed by the Boltzmann distribution under an equilibrium condition. So, again ion distributions are considered in such a way that the no normal flux and distribution of ions are independent of the fluid convection. So, so we can write the distribution of ions as C plus, that is the positive ions, and C minus are governed by this way. So, that means at certain point if I get the electric potential phi, so through that phi one can obtain the ion distribution C plus and C minus given by this way. So, once I know the distribution of ions at any point, so the charge density rho e is Faraday constant into the net ion concentration. So, this molar flux, molar concentration of the ions. So, that means this rho e becomes the 2 f C 0 sine parabolic f by R T phi, where C 0 is the bulk ionic concentration. Now, bulk ionic concentration is governed by the C 0. Now, the equation for electric potential under the Debye Huckel approximation can be written as we have already done, d 2 phi dy 2 equal to k square phi, with k is lambda inverse 2 C 0 f square by R T, which is the Debye length. So, we impose the condition, we consider the origin at that is the x axis is along the central line of the channel, and we consider a axis of symmetry. So, that means this axis of symmetry is valid provided we have both the walls have the same zeta potential. So, this is the condition del d phi dy equal to 0 on y equal to 0, that is along the axis of symmetry. Is symmetry assumption is valid when both the walls have the same zeta potential. With that, if I now solve this equation, so what I get is phi equal to a e to the power k kappa y plus b to the power minus kappa y, as we have done already, and so a minus b equal to 0 as no, not 0, this is equal to zeta, as y equal to 0, phi equal to zeta, and what we have is a e to the power k kappa h minus b to the power minus kappa h equal to 0. Oops, this is 0, but this is I have written wrongly, because so this is as, let us write better way, d phi dy equal to 0 at y equal to 0 under this condition. So, we get this. So, that means this implies that a equal to b. Again, what you have is phi equal to zeta for y equal to h. So, what we have? So, phi equal to, so zeta equal to a to the power kappa h plus b to the power minus kappa h. So, this gives a equal to b equal to zeta by 2 cos hyperbolic kappa h. Okay. So, now if I substitute, so this gives, so phi, which is the equation, so this becomes zeta cos hyperbolic kappa y by cos hyperbolic kappa h. So, this is the electric potential at any point in the slit channel. So, this is the electric potential distribution at any point on the slit channel. So, now we need to find out the velocity of which is we refer as the electroosmotic velocity or EOA velocity from the balance of the charge and electric body force and the frictional drag. So, that will continue in the next lecture.